Welcome to this comprehensive mathematics lecture on sets, designed specifically for students mastering foundational mathematics. Sets form the absolute bedrock of modern mathematical language, reasoning, and logic. Virtually every mathematical branch, from probability and algebra to calculus and computer science data structures, utilizes the language of sets to define collections, functions, and domains. Historically, set theory was developed in the late 19th century by the German mathematician Georg Cantor. Cantor's revolutionary ideas on infinity and set relationships transformed mathematical philosophy, though they initially faced severe opposition. Today, we will master the definition of a set, explore roster and set builder representations, study subsets, empty sets, and universal sets, and visualize operations using beautiful Venn diagrams. Let us begin this conceptual journey. A set is mathematically defined as a well-defined collection of distinct objects. The term well-defined means that given any object, we can decide without ambiguity whether it belongs to the collection or not. For example, the collection of all vowels in the English alphabet is well-defined, containing exactly A, E, I, O, and U. However, the collection of the three most talented singers in the world is not well-defined, as the criteria for talent is subjective and varies between individuals. The individual objects within a set are called its elements or members. We typically denote sets using capital letters like A, B, or C, and denote their elements using lowercase letters like X, Y, or Z. If an object X is an element of set A, we write X belongs to A, using the Greek symbol epsilon. If it does not belong to A, we write X does not belong to A, using epsilon with a diagonal slash. There are two main methods to represent a set. The first is the roster or tabular form. In this form, we list all the elements of the set explicitly, separated by commas, and enclose them within curly brackets. For example, the set of positive even integers less than 10 is written as curly bracket 2, 4, 6, 8, curly bracket. The order of elements does not matter, and repeating elements is avoided. The second method is the set builder form. In this form, instead of listing elements, we describe the common property possessed by all elements of the set. We write, set A equals the set of all X, such that X satisfies a specific property. For example, A equals X, colon, X is a vowel in the English alphabet. This notation is incredibly powerful for representing large or infinite sets where listing elements is impossible. Sets can be classified based on whether their elements can be counted or not. A set is called a finite set if it is empty or contains a definite, countable number of elements. For example, the set of days in a week has exactly 7 elements, and the set of prime numbers less than 20 has exactly 8 elements. In both cases, the process of counting elements terminates. Conversely, a set whose elements cannot be counted because the counting process continues endlessly is an infinite set. For example, the set of all natural numbers, n equals 1, 2, 3, and so on, stretching to infinity. Other examples of infinite sets include the set of all integers, the set of all real numbers on a line, or the set of points on a circle. Although infinite, these sets can still be defined precisely in set builder notation. An empty set, also called a null set or void set, is a set that contains absolutely no elements. It is denoted by the Greek letter phi, or by empty curly braces. The concept of an empty set is fundamental, representing a collection that is simply empty. For example, the set of all months containing 32 days is an empty set because no such month exists in our calendar. Similarly, the set of all real numbers x such that x squared plus 1 equals 0 is empty because the square of any real number is non-negative and adding 1 makes it strictly positive. It is important to note that the empty set is not the same as a set containing the number 0. A set containing 0 has a cardinality of 1, whereas the empty set has a cardinality of exactly 0. Two sets A and B are said to be equal if they contain exactly the same elements. When two sets are equal, we write A equals B. If they are not equal, we write A is not equal to B. The order in which elements are listed does not affect set equality. Furthermore, Repeating elements within a set does not change its identity or elements. For example, if set A contains the elements 1, 2, and 3, and set B contains 3, 2, 1, and another 1, then set A and set B are completely equal. Every element in A belongs to B, and every element in B belongs to A. Understanding equality is crucial when comparing different mathematical descriptions of the same geometric region or solution set. A set A is said to be a subset of a set B if every element of A is also an element of B. We write this relationship as A is a subset of B using a sideways U symbol with a line underneath. For example, the set containing 1 and 2 is a subset of the set containing 1, 2, and 3. If A is a subset of B, but A is not equal to B, we say that A is a proper subset of B, written with a sideways U and no line underneath. This means B contains at least one element that is not in A. The empty set is a subset of every set, and every set is a subset of itself. These two are called improper subsets. Subsets allow us to build hierarchies and nested structures in mathematics. The cardinality of a finite set A is the number of distinct elements present in the set. It is denoted by the notation n of A, or sometimes using vertical bars like absolute value A. For example, if we have a set V containing the English vowels A, E, I, O, and U, the cardinality of V is 5, which we write as n of V equals 5. If a set contains repeated elements, we count each unique element only once. The cardinality of the empty set phi is 0, since it has no elements. The cardinality of a singleton set, which is a set containing exactly one element, is 1. Cardinality is a fundamental measure that helps us compare set sizes, establish one-to-one correspondences, and solve count-based word problems. Given a set A, the collection of all possible subsets of A is called the power set of A, denoted as P of A. For example, if set A contains the elements 1 and 2, its subsets are the empty set, the singleton set containing 1, the singleton set containing 2, and the set A itself containing both 1 and 2. Thus, the power set P of A is the set containing these four subsets. If a finite set A has k elements, then the total number of subsets it can have is 2 to the power of k. This is because when constructing a subset, we have two choices for each element, either included in the subset or excluded. Therefore, the cardinality of the power set P of A is always 2 to the power of n of A. In any mathematical discussion or set theory problem, we usually operate within a basic reference set that contains all objects under consideration. This background master set is called the universal set, denoted by the capital letter U. All other sets under discussion are subsets of this universal set. The definition of a universal set is context-dependent. For example, when studying the integers, the set of all integers z serves as our universal set. If we are studying coordinate geometry, the set of all points in the Cartesian plane is the universal set. In a probability experiment involving drawing cards, the deck of 52 cards is the universal set. Establishing U is vital to define set boundaries and complements. To make set relationships intuitive and visually clear, we use geometric illustrations called Venn diagrams, named after the 19th century English logician John Venn. In a Venn diagram, the universal set U is represented by a large rectangle, and the various sets under consideration are represented by circles drawn inside this rectangle. Relationships between sets, such as inclusion, intersection, or disjointness, are depicted by the spatial positioning of these circles. If two sets share common elements, their circles overlap, creating an intersection region. If they share no elements, they are disjoint, and their circles are drawn separately. Venn diagrams are a powerful tool to conceptualize logical arguments, set operations, and solve systems of overlapping criteria. The first fundamental operation on sets is the union. The union of two sets A and B, denoted as a union B, is the set of all elements that belong to either A or to B or to both. We write this in set builder form as a union B equals X, such that X belongs to A or X belongs to B. In a Venn diagram, The union of A and B is represented by shading the entire area of both circles A and B, including their overlapping region. For example, if set A contains the numbers 1, 2, and 3, and set B contains 3, 4, and 5, then their union contains 1, 2, 3, 4, and 5. The common element 3 is listed only once. Union is the set theoretic analog to logical OR. The second fundamental operation is the intersection. The intersection of two sets A and B, denoted as A intersection B, is the set of all elements that belong to both A and B. In other words, it contains only the common elements shared by both sets. In set builder form, we write A intersection B equals X, such that X belongs to A and X belongs to B. In a Venn diagram, the intersection is represented by shading only the overlapping region where circles A and B cross. If the intersection of two sets is empty, meaning they share no elements at all, they are called disjoint sets. For example, if A contains odd numbers and B contains even numbers, their intersection is empty, and their circles do not touch. Intersection is the set theoretic analog to logical AND. The third fundamental operation is the difference. The difference of two sets A and B, written as a minus B, is the set of all elements that belong to A but do not belong to B. In other words, we take set A and remove any elements that also happen to be in B. In set builder form, a minus B equals X, such that X belongs to A and X does not belong to B. In a Venn diagram, a minus B is represented by shading only the crescent-shaped region of circle A that does not overlap with circle B. Similarly, B minus A contains elements in B but not in A. Note that a minus B and B minus A are generally different sets, demonstrating that set subtraction is not commutative, unlike union and intersection. Given a set A within a universal set U, the complement of A, denoted as A prime, AC, or not A, is the set of all elements in the universal set U that do not belong to A. For instance, if the universal set U is the set of natural numbers 1 through 10, and set A contains the odd numbers, then the complement A prime contains the even numbers 2, 4, 6, 8, and 10. Visually on a Venn diagram, the complement represents the entire rectangular region of U that lies outside set A's circle boundary. Mathematically, the complement A prime equals U minus A. Important properties include a union A prime equals the universal set U, and A intersection A prime is the empty set. In practical word problems, we frequently apply set theory to analyze surveys, logical groupings, and overlapping metrics. For any two finite sets A and B, the cardinality of their union is given by the formula N of a union B equals N of A plus N of B minus N of A intersection B. We subtract the intersection because elements in the overlap are counted twice when we add N of A and N of B. Let's solve a real example. In a group of 50 people, 30 like tea, 25 like coffee, and 10 like both. To find how many like at least one of the drinks, we compute N of tea union coffee equals 30 plus 25 minus 10, which gives 45. The remaining 5 people like neither drink, situated in the complement region. Thank you for studying sets with us today. Creating three-dimensional educational whiteboard content like this takes careful geometric planning, structural code design, and formula verification. If this step-by-step lecture helped you visualize set definitions, operations, subsets, and Venn diagrams, please take a moment to support our free school learning series. Like this video, subscribe to our channel, share it with your friends, and write a comment below suggesting what mathematical topics you would like us to compile next. By joining our digital classroom community, you help us make high-fidelity school science and math lectures freely accessible to students everywhere. Keep studying your dimensions, keep drawing your Venn circles, and we will see you in our next geometry lecture.